So if we actually take a derivative of the left and right side of this equation and this equation, of this side and this side, we get du is equal to 2x dx. And if we integrate both sides of our dv and this, we get v is equal to negative e to the negative x. And this quantity simply disappears. So, now we know what u is, we know what v is, and we know what du is. So we are ready to actually integrate the parts. We get the following result. So all we do is basically see, notice that we have this 1/2 on the outside of the integral, and this entire quantity becomes uv, which is simply this quantity plus this entire result. And we evaluate from 0 to 2. So notice we are not done in terms of integration by parts. We have to apply integration by parts a second time. So to basically solve this, we have to set u equal to 2x, and we have to set dv equal to e to the negative x dx. So, in the fourth step, we apply integration by parts another time. So, let u is equal to 2x, and du becomes 2 multiplied by dx. Now, dv is equal to e to the negative x dx, and if we evaluate the integral of both sides, we see that v is equal to negative e to the negative x. So if we apply the same exact process to this step, we get the following result. So 1/2, we have the bracket negative x squared e to the negative x, which comes from this quantity, and then we apply integration by parts to this, where this is u and this is dv, and we get the following result. Now, if we actually evaluate this integral and we bring out our constants, we get the following result. So 1/2 multiplied by e to the negative x multiplied by negative x squared minus 2x minus 2, and we evaluate from 0 to 2, we get about 0.323, or equivalently 32.3%. So the probability of finding our electron within the spherical region of the Bohr radius r0, which is equal to 5.29 times 10 to the negative 11 meters, is given by 32.3%. Let's suppose that we are asked to use the radial probability distribution to calculate the most probable location of our electron inside the ground state of the hydrogen atom. So basically, what that means is we have to use the following equation for the radial probability distribution to calculate where our electron is most likely found at any given moment in time around that nucleus of the ground state hydrogen atom. So, recall that the radial probability P depends on R, where R is the distance away from the center of the nucleus of the atom. And P with respect to R is equal to 4R squared divided by R0 cubed multiplied by E to the negative 2R divided by R0, where R0 is simply Bohr radius. It's 5.29 times 10 to the negative 11 meters. So basically, if we take this equation and we plot it on the xy axis, we get the following green curve, where our x-axis is the distance r away from the center of the nucleus of the atom, and our y-axis represents the value of the radial probability P. Now, P only really depends on R. Now, if we examine the following curve, we see that the highest point on the curve is given by this point, and this point represents the highest value of the radial probability, and this is in fact the most probable location. So, if we draw the following vertical line directly downward, this unknown R quantity represents the maximum or the most probable location location of our electron, which corresponds to the maximum value of the probability density, the radial probability. So basically, if we use a bit of calculus, we can find what this R is. So notice if we look on the curve, at this point, our slope of the curve changes from positive to negative. And exactly at this position, the slope of the curve is equal to 0. Now, by definition, the derivative of our function is equal to the slope at that point. So if we find what the derivative is at this point, and we set the derivative equal to 0, we can solve for the R, as we'll see in just a moment. So basically, since we know what this equation is for the radial probability distribution, we can use calculus to find the value of R such that the PR is a maximum. And the PR is a maximum at this exact position. So that's the peak value. Notice that the slope of the curve at this maximum value is equal to 0. This means that the derivative at that point is also equal to 0, because by definition, the derivative is really the slope at that position along the curve. So basically, we want to find the derivative of this equation, but this equation consists of two different functions. So let's suppose that this function, we let this function equal to f of r, and this function is equal to g of r. So if f of r is equal to 4r squared divided by r naught cubed, and g of r is equal to e to the negative 2r divided by r naught, then we can apply the product rule to calculate what the derivative of PR at this position given by R. So the derivative of P at this location R is equal to the product of the derivative of F multiplied by G of R plus our F of R multiplied by the derivative of G with respect to R. So what exactly is the derivative of F? The derivative of F is simply 2 multiplied by 4, or 8 multiplied by R, divided by R naught cubed. And this quantity is simply given by this. So we have 8R divided by R naught cubed multiplied by the exponent e to negative 2R divided by R naught. And we add that to F of R, which is simply this quantity multiplied by the derivative of this guy. So we have negative 2 divided by R naught multiplied by e to the power of negative 2R divided by R naught. So we add these two quantities and we set them equal to 0 because the derivative of our electron within our atom. And the principal quantum number can take a value that is any positive integer. So basically, n can equal to 1, 2, 3, 4, 5, and so on. Now, if we know what the principal quantum number is of our electron, and we know what the energy is of the electron found in principal quantum number n equals 1, then we can use this equation to calculate what the energy is of the electron found within the nth principal quantum number. So basically, the first principal quantum number, the principal quantum number tells us the energy of our electron within the atom. Now let's move on to the second quantum number. The second quantum number is known as the azimuthal quantum number, or the orbital quantum number. And the orbital quantum number is given by lowercase l. And the orbital quantum number is related to the angular momentum given by uppercase L of the electron within that atom. Now, what exactly is the meaning behind So basically, the orbital quantum number describes the shape and the size of our orbit that we're dealing with. It describes the shape and the size of the electron cloud that is produced by that electron. Remember, the electron cloud basically gives us the most probable location of our electron within our atom. So it gives us the shape of the most probable location in which our electron is actually found around that atom. Now, what exactly are the values that the orbital quantum number can take? Well, L is readily given by this equation. So basically, if we know what the principal quantum number n is, we can determine the number of orbitals that our atom has. So L is equal to 0, 1, 2, 3, 4, and all the way up to n minus 1, where once again n is the principal quantum number. For example, if we know that some given atom has 3 principal quantum numbers, so n is equal to 3, then that means by using this equation we see that our atom has 3 different orbital quantum numbers. So L can either be equal to 0, 1, or 2, where each one of these quantities represents its own shape and size and type of the orbital, the electron cloud that we are dealing with. For example, L equals 0 corresponds to a spherical electron cloud, a spherical orbit, as we'll discuss in a future lecture. Now, earlier we said that the orbital quantum number is related to something known as the angular momentum of our electron. Now, the relationship between the orbital quantum number L and the angular momentum given by uppercase L is given by this equation. So the angular momentum squared is equal to h bar squared multiplied by L multiplied by L plus 1, where L is the orbital quantum number, h bar is a constant that is related to Planck's constant, and L is the angular momentum. So, we see a very important trend. Basically, the principal quantum number determines the number of orbitals we can have, the number of orbital quantum numbers that any atom can have. Now, let's move on to the third quantum number we call the magnetic quantum number, that is given by M with the L subscript on the bottom. Now, if the shape, the size, and the type of our orbital, the electron cloud around the atom, is described by the orbital quantum number L, then the orientation and the direction of this orbital, the electron cloud in the three-dimensional space, is given by the magnetic quantum number. So basically, the orbital quantum number describes the type and the size and shape of our orbital, but the magnetic quantum number designates the orientation and direction of our orbital in the three-dimensional space. So the magnetic quantum number tells us the direction of the angular momentum, while the orbital quantum number describes the magnitude of our angular momentum. Now, what exactly are the values that the magnetic quantum number can take? So basically, this is the equation that tells us the different values that the magnetic quantum number can take. So in the same way that the principal quantum number determined the number of orbital quantum numbers, the orbital quantum number determines the number of magnetic quantum numbers. So ML is equal to negative L to positive L. So to see what that means, let's suppose that, for example, an electron is found within orbital L equals 1. So because we know what the orbital quantum number is, because L is equal to 1, we know that the possible magnetic quantum numbers are negative L, 0, and positive L. So basically, if L is equal to to 2, then our ML can be -2, -1, 0, +1, and +2. So we see that for any given orbital quantum number L, there is a certain specific number, a certain limit to how many magnetic quantum numbers there are. That is, if we know what the orbital quantum number is, if we know what the shape of that orbital is, if we know what the shape of the electron cloud is, then we know there is a limit to the number of orientations that this orbital can take, this orbit can take within the three-dimensional space. So, for example, for L equals 1, there are 3 different orientations. And this is known as the space quantization of the magnetic quantum number. So basically, the fact that any given orbital has a certain number of orientations, has a limit to the number of orientations it can take, this is known as space quantization. And finally, the last and fourth quantum number is known as the spin quantum number, and this is given by M with the S subscript. Now, basically, any one electron within any given orbit can have one of 2 possible spin numbers. So any electron can have 2 possible spins. It can either have a spin up, in which case the ms is equal to +1/2, or it can have a spin down, in which it has an ms that is equal to -1/2. So let's examine the following example that deals with determining the angular momentum and energy of an electron within a hydrogen atom. So let's begin. Suppose we have an electron inside a hydrogen atom whose orbital quantum number L is equal to 5. So we want to determine what the angular momentum is in part A and what the energy is in part B of that electron, assuming that the energy of our electron is equal to 13.6 electron volts when our principal quantum number N is equal to 1. So let's begin with part A. So to calculate the angular momentum of the electron, we have to apply this equation. So the magnitude of the angular momentum L squared is equal to h bar squared multiplied by L multiplied by L plus 1, where lowercase l represents the orbital quantum number, and in this case, lowercase l is equal to 5. So let's isolate L on the left side by taking the square root of the left and right side. We get the following result. So L is equal to h bar, which is equal to 1.05 times 10 to -34 joules multiplied by seconds, and we multiply that by the square root of L, which is 5, multiplied by L plus 1, which is 6. So 30, we take the square root of 30 and multiply by h bar, and we get about 5.75 times 10 to -34 joules multiplied by seconds is the angular momentum of our electron within orbital quantum number L equals 5. Now, let's move on to part B. To calculate what the energy is, we take our energy for principal quantum number N equals 1 and divide that by N squared. Now, E1 is equal to 13.6 electron volts, and N is equal to L minus 1. So we know that L is equal to 5, and 5 minus 1 is equal to 4. So we have 13.6 electron volts divided by 16, and that gives us about 0.85 electron volts. So this is the energy of that electron, and this is the angular momentum of that electron when it's found inside the orbital quantum number L equals 5 inside the hydrogen atom. In this lecture, we're going to look at the selection rules that exist in quantum mechanics when electrons transition between energy states. So let's suppose we have an electron within some given atom, and that electron gains a certain quantity of energy in the form of a photon of light that has just the right frequency, so our electron jumps from a lower energy state to a higher energy state. Now, conversely, the opposite can also take place. So basically, if an electron transitions from a higher energy state to a lower energy state, in the process, it will release a photon of light that has a certain given frequency, as shown in the following diagram. Now, in quantum mechanics, we know that certain electron transitions are more likely to take place than others. The ones that have a high probability of taking place, these transitions are known as the allowed transitions. And the transitions that are very improbable, the ones that are less likely to take place, are known as the forbidden transitions. And in quantum mechanics, a set of rules exist known as the selection rules that basically tell us which transitions are the allowed transitions. And these rules are given by these two rules. So, rule number 1 tells us that delta L, or the change in orbital quantum number during our transition, is either positive 1 or negative 1. So basically, positive 1 means that our electron jumps from a lower to a higher energy state, and a negative 1 means our electron jumps from a higher energy state to a lower energy state. So basically, this rule tells us that by more than one orbital quantum number, and the change in L cannot be equal to 0. Now, the second rule tells us that the change in the magnetic quantum number is either 0 or positive or negative 1. Now, to see exactly what we mean by these two rules, let's suppose we have an electron that is found in the 2p orbital of the hydrogen atom. So, here we have a diagram of the 2s orbital and the 2p orbital. So what exactly is the 2s orbital? So the 2s orbital has a principal quantum number of n equals 2. It has an orbital quantum number of L equals 0, and our magnetic quantum number ml is equal to 0. Now, in contrast, the 2p orbital basically has 3 different orientations. We have one along the x-axis, one along the y-axis, and one along the z-axis. So the one along the x-axis has a magnetic quantum number of ml equals negative 1. Now, our y-axis oriented orbital has a magnetic quantum number of ml equals 0, and the z1 has an ml of plus 1. Now, for each one of these orbitals, the principal quantum number as well as the orbital quantum number is exactly the same. The difference lies in the magnetic quantum number. Now, the question that we want to examine is the following. Suppose our electron is found in either one of these orbitals. Let's suppose it's found in the 2pz orbital. The question is, if we follow these selection rules, can our electron actually jump from our 2pz orbital to the 2s orbital? So from the selection rules, we see that the electron can in fact jump from any one of these 2p orbitals to the 2s orbital. And the reason is, if we look at the a change in the orbital quantum number, we go from L equals 1 to L equals 0. And this corresponds to a delta L of negative 1. So that means regardless of whether our electron is found in the 2py, the 2pz, or the 2px, that electron can in fact transition from either one of these orbitals to the 2s orbitals and release a photon of light. Now, on the contrary, let's suppose our electron wants to transition from the 2pz to the 2py, or from the 2py to the 2px. Can that actually take place? So notice that the electron cannot actually jump between one of these three 2p orbitals, and that's because in such a case, the change in the orbital quantum number, delta L, will be equal to 0, and delta L cannot actually take place. So basically, these transitions are known as the forbidden transitions, and this transition, as discussed earlier, is known as the allow transition. Now, once again, even though this transition is known as the forbidden transition, that basically means it can actually still take place, but it is very unlikely. There is a very small probability that such a transition will actually take place, versus in this case, where there is a very high probability that such a transition can actually take place. So once again, these rules, known as the selection rules, are in place and are used in quantum mechanics to determine which electron transitions are the probable ones and which ones are the improbable ones. Every single electron has an intrinsic property known as the electron spin, and it's the spin of that electron that creates something called the electron's magnetic dipole moment. Now, before we get into that, let's recall, generally speaking, how a magnetic dipole moment is formed. So recall that a current loop forms a magnetic dipole moment that is given by this equation. So basically, we have a conducting loop of wire that carries a positive electric current, let's suppose, in a counterclockwise direction. And as it travels, it will basically form a magnetic dipole moment that is given by mu that points upward perpendicular with respect to the area that our loop of wire encloses. Now, if the area is given by A, then the magnitude of the magnetic dipole moment mu is given by taking the product of I, the current, and A, the area. So this gives us the magnitude of the magnetic dipole moment formed by the current loop. Now, what about the electron magnetic dipole moment? Well, if we treat our electron as if it was a particle, then we see that the electron actually creates its own electric current that loops or orbits the nucleus of the atom. So let's suppose the nucleus of the atom is at the center of this loop. So basically, we have the electron, which now moves not in the counterclockwise, but in the clockwise direction, and as it moves, because it has a negative electric charge and it moves with a very high velocity, it basically creates a continuous negative electric current. And that's exactly why we have to reverse directions. So if we have this negative electric current that is created by the charge on that moving electron, if we have this negative electric current, it will create a magnetic dipole moment that also points upward perpendicular with respect to the area. Now, in our discussion on classical mechanics and the electron's orbit around the nucleus, we were able to show that if we take this equation, we can actually obtain equation 1, where equation 1 gives us the magnetic dipole moment of the electron as it orbits the nucleus of the atom. So mu is equal to E multiplied by V multiplied by R divided by 2, where R is the radius of the orbit, v is the velocity of that electron in orbit, and E is the charge on that electron given by negative 1.6 times 10 to negative 19 coulombs. Now, anytime we have a particle with the mass m that is undergoing rotation or angular motion, that object with mass m and velocity v and radius r creates an angular momentum that is given by this equation. So we take the product of the mass m, the velocity v, and the radius of orbit r, and we get the angular momentum that is created by that electron's spin. Now, if we rearrange this equation and solve for the velocity, we see that the velocity of the electron as it spins around is equal to L divided by m times r. Now, let's call this equation 2. If we take equation 2 and plug it into equation 1 by basically replacing the velocity with L divided by m times r, we get this result, and notice the r's appear on top and bottom. We can cancel the r's, and we get that the magnetic dipole moment that is created by the electron is equal to E divided by 2 times m multiplied by L, the angular momentum. So let's call this equation 3. Now, this gives us the magnitude of the magnetic dipole moment. What about the direction? Well, the direction of the magnetic dipole moment of the electron lies along the same axis as the direction of the angular momentum. But because the electron has a negative charge, and the charge on this current is opposite to this charge, which is positive, that means they point along the same axis, but in the opposite direction. So if L points up, the magnetic dipole moment points downward. So once again, the angular momentum L of the electron points along the same axis as the magnetic dipole moment mu of the electron, but in the opposite direction. So that means we have to put a negative in front of this term. And we see that the magnetic dipole moment of the electron is equal to negative E divided by 2m multiplied by L, where m is the mass of that electron. So basically, this gives us the electron's magnetic dipole moment created by that spin in terms of the angular momentum of that electron. Now, we can also express the electron's magnetic dipole moment in terms of the orbital quantum number. Now, in our discussion on quantum numbers and the quantum mechanical theory of the atom, we were able to show, or actually we simply said, that the square of the angular momentum L is equal to h bar squared multiplied by L plus 1, where h bar is a constant and L is the orbital quantum number. So basically, if we take the square